Alright folks, today we're going to talk about electricity, and electricity itself is a very large topic. There's a lot of things to talk about. We can talk about static electricity, electricity, magnetism, electromagnetic forces, we can talk about circuitry, all those types of things, but what we're going to do here is we're going to get an overview of kind of all of that. We're going to start just by talking about what is the elementary charge, like what is a positive or negative charge. We'll talk a little bit about what is current and voltage. We'll look at series and parallel circuits, and we'll talk a little bit about electromagnetic force and fields. So we're not going to dive real deep into any of those concepts, but we're going to talk briefly about each one in the notes. As we work through some of the material here in the future, we'll pick out each individual topic and focus on it a little bit more direct. So here it is. The first question that's proposed in the notes is asking exactly what is electricity. Well, basically electricity is the presence or flow of an electrical charge. And then you would lead to the question as what is electrical charge? Electrical charge would basically be the imbalance of electrons versus protons. So when we start talking in language like that, it kind of brings us back to chemistry class. Maybe not so much physics, but when we're looking at what is elementary charge, you got to look at the structure of an atom just a little bit. Atoms are made of protons, neutrons, and electrons. So inside of the nucleus they have protons and neutrons. Protons have a positive charge, neutrons have a neutral charge, and electrons have a negative charge. So when you're talking about the total charge of an atom, we're normally looking at the difference between the protons and electrons. If they're equally balanced in charge, if there's 6 protons and 6 electrons, they would say that the atom is neutral. It has a total charge of nothing, 0. We would say it's balanced. The one positive and the one negative of each cancel each other out. You start looking at, this is what they would call ions, atoms that have a positive or negative charge. If we have an imbalance of them, for example, if you have 5 protons and we only have 6 electrons, this is going to be leaving us with 1 extra electron, which means that this would have a total charge equal to -1 if we looked at this thing as a whole. So if you've ever, see diagrams of atoms, or if you've even seen symbols, and sometimes you'll see +1, +2, -1, +3. Normally what they're talking about there is the ion state, so what is the imbalance? Are there more protons or more electrons? And then for the next one here, if you're going to have something that's going to be positively charged, of course you need to have more positive charges than negatives. So let's say we had 6 protons and only 5 electrons, and of course this is going to have a +1 charge. Now what does this mean in the world of electricity? Well, the thing that actually moves most easily, or is most easily separated from an atom, is the electron. Remember, the electrons are on the outside. They have less mass, although equal charge to the proton, but those can much more easily or readily be moved around from one point to another. So again, the definition for electricity was the flow of electrons, basically. So they can only flow if there's an imbalance in charge, but it's still the electron that's actually in motion. So when we talk about current, and whether it's storage of voltage and charge inside of a battery, or talk about current flowing through a wire, it's often referred to as what's really happening with the electron. Where is it moving to and from, and how quickly, and how many are there, and so forth. So when we talk about static charge is something that can be demonstrated quite easily. I'm sure everybody in here has had hair that's been staticky, or maybe your clothes. If you in the winter time, especially when it's dry out, you might notice that you put a shirt on or something and it kind of sticks to itself. The whole idea there is when different objects are rubbed together, or there's some way that energy is put into the system, or maybe heat, or physical contact, or whatever, on the molecular level, or even the atomic level, electrons actually get moved around from one place to another. And there is something called the triple electric series, which kind of denotes, based on the type of material it is, which one will more easily gain or more easily lose electrons. So this doesn't have every piece of material or matter that we deal with in real life, but it does have a fairly high number of items on the list. Things that are further high up on the list, on the top of this list, are things that would likely take on a positive charge, which means they would most easily lose electrons. So let's say, for example, I had a sample of wool, like a pair of wool pants, or just like a wool blanket or something like that. And let's just say we went further down on the list here somewhere, and let's just say you looked at gold. gold is further down on the list toward the negative side. Gold will more easily want to gain electrons or take electrons in than give them up. So if I took the piece of wool and took the gold, for whatever reason, I'm going to polish the gold nugget or something and make it look nice and shiny, a static charge is going to build up. And the way that that charge separates or divides is the gold, since it's lower on the triple electric series, will want to gather electrons, and the more electrons you have, the more negative charge you have. So this is going to definitely want to take on a negative charge, a positive charge. Because remember, it's not like the positive charge is going to the wool, it's that the negative charge particles are leaving the wool, therefore leaving it in balance. So the things that actually physically move back and forth are the electron again. So don't think that a proton, it's not like protons are leaving the gold and going to the wool. That disturbs a whole bunch of properties of chemistry. If you change the number of protons, you're changing the actual element that it is, and so forth. So that's not what's happening. So we talk about like charges versus different unlike charges and what happens as far as force or motion, or what way do they actually move. So I think even as a younger individual, you probably have played with magnets or just had the whole idea that, opposites attract and like things repel. So in this diagram, it's just showing if you had, two atoms or two particles or charged things, whatever it would happen to be, if they're both the same, they want to separate. And it doesn't matter if they're both positive or both negative, but they want to get away from each other. On the other hand, if you have things that are oppositely charged, something that's negative, something that's positive, they're going to want to naturally move together. So what happens if we start looking at items or materials that will easily conduct electrons? So we're talking about the difference between insulators and conductors. Conductors are something that will allow electrons to flow through it easily, and insulators would be the complete opposite, something that doesn't allow electricity or electrons to flow through it very easily. And some of the things that are very good conductors are normally metals, silver, gold, copper, steel, and seawater. And seawater, you might think, well, that's kind of weird. It's the fact that there's salt in it. Water can be a conductor too, but if you put salt in it, it helps the conductivity. And then electrical insulators, rubber, glass, oil, diamond, and dry wood. There's other things, obviously, that are insulators, but these are some of the most common. So if you've ever used electrical components, if you've ever looked at a wire per se, normally wires that are insulated, the outside's wrapped with some sort of a wire, and the inside's normally copper. Sometimes it's aluminum, or it could be combinations of other types of metals, but particular copper is probably the most common, and then the coating on the outside is some sort of a plastic or a rubber. Which makes sense, because if we're trying to contain electricity and get it to go from one point to another, we don't want to lose it along the way. All right? The way a battery works, or even the outlet in the wall, basically what you have in order to create electrons to flow is you need an imbalance of them. You need to have a whole bunch of them somewhere, and you need a place that doesn't have a whole lot of them so they have a place to go. And if you can get that current to move, you can do a whole bunch of things. You can actually create force with that. So if you can create force or use it to produce energy, you can make light or make things move. And of course, how all that works is a little more complicated, but that's just the general idea of it. So if you have something that has a bunch of electrons on one side, and on the other side it has something that doesn't have a lot of electrons and really wants it, we would say, the one side of the battery is negative and the other side is positive. It's confusing, and you will find in various sources that electron flows, they will say the electrons or current flow in a given direction. Now, the reality of it is electrons, if you're looking at the electron flow, and this is going to be different than current, because sometimes it's stated differently, the electron flow is always from negative to positive. It has to go from negative to positive, because that's what electrons do. Remember, the electrons are the ones that move. So when we talk about the negative side versus positive side, that's the negative charge versus positive charge. Where the electrons are and where the electrons want to go is always from negative to positive. Now, I can guarantee you can search online, you're going to find places and diagrams and even simulators and things that we're going to use too, and they're going to show a picture of a battery, and the battery might look like this, and I'll put, a probe on one side, an anode on the other, will be listed as positive or negative like this, and I can guarantee that they're going to draw it going like this. They're going to say, the current flows from positive to negative. Okay, they call this conventional flow, and most models and a lot of models are set up that way to say that the conventional flow goes from positive to negative. Intuitively, it kind of makes sense. We seem to think of things going from positive to negative, plus to minus. Remember, positive things don't move in an electrical circuit. A proton does not move from here to here. An electron flows from one point to another. So really what's flowing is the electron, and that always goes from negative to positive. So whether the electrons are really over here and go in here, and they label this as the positive end or the negative end, we'll let that be as is. Normally, unless when we start talking about diodes or things that only let flow go in one direction, who cares if it's flowing this way or flowing that way as much, but the current is still going to flow and we can still do calculations on what that current actually would be. So, not to confuse you, but this versus this, it is different. We're going to look at basic electrical circuits, primarily in the combination of parallel and series circuits. So just to talk a little bit about what those are, in a circuit diagram, they're going to label some sort of a voltage source. So a lot of times they'll label that as Vs, but basically this is the same thing as a battery. It'll show a positive and negative side, and just like I'm talking about the conventional flow, they're showing that the current goes from the plus to the minus. So the I here is representing current, R is representing resistance, and the V is representing voltage. So these three things are the fundamental variables that we're going to use when talking about electrical circuits. You're going to have voltage, you're going to have current, and you're going to have resistance. So when you're working with these, it's good to have an idea what each one of those really is. If you think of it, voltage is kind of like the imbalance of your different charges. So the more voltage you have way more of these electrons that want to get to the positive area wherever it goes. When you're talking about current is the flow of electrons. So if you want to think of this like a hose, or down here in this diagram, they show it like a container of some sort, but the voltage is trying to push through at a certain rate, and the rate at which it is flowing is known as the current. So the faster something flows, the more current it would have. If it's not flowing as fast, it wouldn't have as much current. And then the ohm is known as the resistance. So this is the voltage here, this is the current pushing through, and then this is the resistance here. The resistance is something that causes a problem for the current to flow. So if you've ever been watering the lawn or using a hose, like when the hose is open, there's low resistance and a lot of water can flow out. If someone went over and put a kink in the hose or squeezed down the hose a little bit, it would slow the flow down. The electrons wouldn't want to flow through there quite as easily, and that's kind of what resistance is. Now, when you have things of resistance, we generally just call them a resistor. In the real world, a light bulb could be a resistor. I mean, a motor could have a certain amount of resistance. Different things connected along the way are going to be troublesome so that the current doesn't want to flow as much. But whenever you have resistance, you normally can somehow be getting something out of it. I mean, heat or light or work or whatever it may be. So in terms of conservation of energy, it kind of all goes full circle. So in a parallel circuit, they talk about the resistors being lined up so that the voltage on each side of the resistor remains constant. So if this is our voltage source, and let's just say, for example, this is a 9-volt source, all the way on this side we have 9 volts, and all the way on this side you basically have 9 volts. So going across each one of those resistors, the voltage is the same. Now, if the resistance of these is different, like maybe this hose has a very low resistance, this has a medium resistance, and this has a very high resistance, this would be like a very large opening, a medium-sized opening, and a really small opening. More electrons are going to flow through this one than this one, and even less through this one. So again, think of the person here kind of restricting off the flow. If we talk about a series circuit, everything only has basically one path for it to go through. So it's got 9 volts here. The voltage across each one of the resistors is not necessarily the same, because there's a voltage drop as you go across from one to the other. However, the thing that is kept the same, if you added up all of these resistances, it would be as if the battery was trying to push all of these through one one type of resistance, and the current would remain the same. So if this happens to be, 2 amps here, it would be 2 amps here, and 2 amps here, and 2 amps here. In this, an awful lot, this is known as Ohm's law. And Ohm's law shows the relationship between voltage and current and resistance. So we're going to do some example problems with those here, so you guys get a little bit better understanding on how to do this. So using Ohm's law and some of the previous diagrams here, we're going to calculate some of the missing information that is labeled. So in example number 2, they give us a voltage source. They tell us that the voltage is equal to 110 volts. They show the current to go, in this direction. Going from here to here, it's going to flow through the resistor, it's going to go this direction. They want us to figure out what the current is. Well, looking at Ohm's law, it can basically be written 3 ways. We could say voltage is current times resistance, or we could say that resistance is equal to voltage divided by current, or we could say that the current is equal to voltage divided by resistance. So depending on what unknown you're looking for, we could choose one of the 3 variations of the equation. In this example, we're looking for I. Now, this only has one resistor, which is good. It makes things a little bit simpler. We know that's the total voltage. We know this is the total resistance. So if we want to figure out the total current going around, which is going to be constant because this is a series circuit, I'm going to take the 110 volts and I'm going to divide it by this 2200 ohms. And you'll see the symbols that we use as we go along and kind of adapt to them. An ohm kind of looks like an upside down horseshoe here. The voltage we use a V, and then for current we're going to use A. If I divide this out, the 110 volts by the 2200 ohms, I get a very small 0.05 amps, which is the flow of electricity going through it that way. For example number 2, they give us the amps, and remember the amps are labeled as I, and then it gives us the ohms here, which gives us the resistance, and then they're asking us to figure out the voltage. So the voltage here is now the unknown. And again, we're just talking about a single resistor, so we're trying to keep things fairly simple. Look at the form of the equation that you want to use for Ohm's law. The voltage is going to be equal to current times resistance, so I'm going to just plug in what I got. We got 2 amps, and we got 13 ohms. And if I plug those 2 things together, I get 26 volts. So the voltage of whatever this battery source is, or voltage source is, has to be at least 26 volts in order for the 2 amps to flow through the 13 ohm resistor. We start to get into some more difficult examples. Sometimes there's going to be more than one resistor in a circuit. And if that's the case, we have to do some equivalent resistance calculations, and there's a few ways to kind of go about it. I did tell you that in a parallel circuit, the voltage on each side of this is going to be the same, however the current will change. So in order to figure out the current through each of these paths individually will change. What I'm going to ask us to try to find for this one is I'm going to ask us to try to find the current in this location here. I'm going to call it current 1. Because the current across all of these wires here and here, it's going to be the same. Current 1 here, current 1 here will be the same. But the flow, if you could imagine this like water, some of it's going to go here, some of it's going to go here, some of it's going to go here. So the current across each one of those resistors is definitely not going to be the same. So we're going to just try to find overall current across the whole circuit. So with that said, the resistance in a parallel circuit looks like this. You do 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3. Now this might seem kind of confusing as to how or why we got them all flipped over. The way this works though is I'm going to have something that looks like this. I got 1 over 90 plus 1 over 45 plus 1 over 180 is going to give me a certain value. Once I get that certain value, it needs to be inverted. I need to do that value, or 1 divided by that value to actually get the overall resistance. If I do that, this tells me that the overall resistance is 25.7 ohms. So that's the resistance total. Once I have that, if I want to figure out the current, in the first spot, I'm going to take the total voltage, which was 9 volts, and I'm going to divide it by the total resistance, 25.7 ohms, and this is going to give me a value of 0.35 amps. So that's going to give me the current at that spot. Another way that I can figure out the total current going through the system is I can look at the current individually going across each of the resistors. For example, I'll label this as current A, current B, current C. So since I told you that the voltage on each side of this resistor is going to be the same, but the current is not, we can simply just take a look at these individually. For example, the current of going across resistor A is simply going to be equal to the 9 volts divided by 90 ohms. If I divide that out, I get 0.1 amps. If I take a look at the current going across part B here, which is resistor 2, I'm going to have 9 volts divided by the 45 amps, or sorry, 9 volts divided by 45 ohms, and if I divide that out, this gives me 0.2 amps. So this is putting me at a total of 0.3 amps. And if I take the last one, if I look at current C, I'm going to take the 9 volts and divide it by the 180 ohms, which is going to give me even a smaller current. This gives me 0.05 amps. And if I look at all of these together, I got 0.1, 0.2, 0.05. If I add those three things together, you'll see that I also get the 0.35 amps from the beginning. So Kirchhoff's rule, which we won't talk about a whole lot, but Kirchhoff's rule basically says whatever current is flowing from one part of the circuit has to equal the total combination of current flowing through any other part of the circuit, because it's all connected. And for example number 5, this one's talking about a circuit that's a combination of series and parallel circuits. So there's kind of a few ways to go about this. One thing I'll ask here, we're just going to look at the current, the main current leaving the battery and coming back into the battery. When you're adding combinations of parallel and series circuits, if this was just, for example, if this was not here, to the right-hand side, we would just consider this to be in series. You would have a resistance of 20 and 30 and 20. You could just add them together, 50, 60, 70, and we could figure out the current by looking at that voltage with the total resistance of 70. When I add this resistor in over here, you can't mistake and say, okay, I had 70 before and add another 50 to it, the total resistance is equal to 120. This portion of the circuit is actually parallel. So if I'm going to look at the equivalent resistance here, I got to look at 1 over R is equal to 1 over 30 plus 1 over 50. And if I sum all of that up, if I add a 30th plus a 50th, and then do the inverse of it, if I do 1 divided by that value, equivalent resistance of 18.75 ohms. So basically I could replace these two with an equivalent resistance of 18.75. And you might think, well, how is it lower? How is it a lower resistance? Well, you got to remember it's got two paths to flow through. So even though 50 and 30 are both higher than 18.7, the fact that there's two roads or two paths for them to go, it acts as if the resistance here, you know, how much resistance there is to go there, into it or out of it, it actually seems less because there's more paths for it to go. So it does kind of make sense that the number's a little bit lower than before. So now if I want the total resistance of this full circuit, I could look at everything added together. I can do the 18.75 and the 20 ohms and the 20 ohms here, which is going to give me the total resistance if I'm calculating the current at position 1. If I add that all together, I get 58.75 ohms. Now that's going to be the resistance at this point. If I came here or somewhere over here or wherever it would be, the resistance of course changes, but we're trying to figure out the resistance as it comes flowing out of the battery, just to find the current at that location. So if that's the case, then I want to find the current. We're going to take the voltage of 10 volts and we're going to divide it by the total resistance, 58.75 ohms. And if I do that, I get something like 0.17 amps. So nowhere in the circuit, aside here and right down here on this side of the resistor, the current has to be less than that in some place. Even as it flows through these two resistors, the combination of these two has to only equal 0.175. So there's different ways for going about how to calculate the balance of it, but you can do it using proportions is one way that you can do it. You can do voltage drop across there to try to find the total voltage here, and then calculate it across using Ohm's law, and so forth. Talking about electric fields and magnetic fields, one thing that is true is anytime you have an electrical current, if you have electricity or electrons flowing through a wire, they will produce a magnetic field. And one of the ways that you can talk about, and the right-hand rule would say that whatever direction the electric current is going in a wire, if you use your right hand to wrap it around, the direction of the magnetic field would be in the position of your four fingers, not including your thumb, your index, ring, middle finger, and pinky finger. This starts getting into electromagnetic force. You know, if you have a certain charge within an electric field, you can actually create motion, or you can get things to move. And one of the most common applications for that is to talk about how an electric motor works. So you'll see that in the diagram that you guys have below. So in terms of an electric motor, we're talking about the right-hand rule again. Instead of just this being current and this being the magnetic field, we start talking about electromagnetic force, where you can use the index finger to represent the current. You can use your middle finger to represent the direction of the magnet, and then your thumb will represent the direction of force that's applied to an object. So this is a real basic example of how an electric motor works. You can see the red arrows showing the direction of the current going through the wire. There's some charge put on each side of what they would call a commutator, which will alternate the direction of current through this wire. If I point to this direction here to the right, the magnetic field going from north to south is noted by B. The force is pushing up, which causes the wire to go up. If we're on the other side and I'm using the right-hand rule, the current is going this way, and the magnetic force is going that way, so I kind of have to flip it upside down, and the force ends up pushing it down. So this is causing something to spin in a circle. The commutator will alternate the current as it gets to about 90 degrees and just keeps repeating itself, and it pushes poles, pushes poles, pushes poles. That's the basics for how an electric motor works, and we'll look at it a little bit more in depth. We'll talk about brushless motors versus brushed motors and AC/DC motors and everything else. But that's kind of the overview for electricity, and stay tuned for more work to come. We'll have some more stuff later on, and if you guys got questions, please feel free to let me know. Thanks a lot, and have a good day.